Something extraordinary is happening in our cosmic backyard. Something that could rewrite what we thought we knew about how the universe connects itself. A new traveler has entered the scene. The interstellar comet 3I Atlas, a mysterious object that came from beyond the gravitational reach of our sun and is now sweeping past Mars. For the first time in human history, orbiters around another planet are not just studying their host world, they're turning their gaze outward toward a visitor that was born in another star system. Think about that for a second. We're watching alien matter formed billions of years ago in a completely different solar neighborhood, gliding within range of our machines on Mars. This isn't a science fiction script. It's real. It's happening right now, and it's quietly unfolding, while most of the world isn't paying attention. NASA's Mars Reconnaissance Orbiter, the European Space Agency's Mars Express and ExoMars Trace Gas Orbiter, and China's Tianwen 1 have all joined forces for an unprecedented observation campaign. On October 3, 2025, Atlas passed just 30 million kilometers from the red planet, close enough for their cameras and spectrometers to catch its faint coma and the shimmering trail of dust and gas stretching behind it. The Mars orbiters have become our cosmic window, not to the past of Mars this time, but to the distant beginnings of another solar system. But what makes this comet so special? Why has it triggered the attention of every major space agency? The answer lies not only in its origin, but also in its timing. Only 2 interstellar objects have ever been confirmed before, Oumuamua in 2017 and Borisov in 2019. One was bizarre and unpredictable, a shape-shifting rock that defied explanation. The other behaved more like an ordinary comet. But 3I Atlas is something in between, active yet chemically alien. It offers a once-in-a-lifetime chance to study how matter born around another star behaves as it interacts with our sun. Detected on July 1, 2025 by the Atlas Survey Telescope in Chile, the comet first appeared as a faint, unremarkable speck. But when its orbital path was calculated, astronomers realized something astonishing. It wasn't bound to the sun. This wasn't one of ours. It was a true interstellar traveler moving on a hyperbolic trajectory that would send it hurtling through our solar system only once before vanishing forever into deep space. That revelation changed everything. Within weeks, agencies from 3 nations coordinated to turn Mars into a temporary observatory, positioning orbiters to capture every photon of light reflected off this icy messenger. And here's the most mind-bending part. The data they collect could reveal the chemical fingerprints of a world that formed around a completely different star. Imagine knowing what alien ice and dust are made of, not through fantasy but through real spectroscopy and imaging done from orbiters we built. Scientists say the comet's composition could teach us how planetary systems eject material into interstellar space, and how those fragments evolve over millions of years of radiation exposure and cosmic travel. But as with any breakthrough, there are mysteries already emerging. Why does 3I Atlas emit mostly carbon dioxide instead of water vapor, unlike comets from our own solar system? What does that say about the temperature, radiation, and environment of its birthplace? And most intriguingly, could these frozen fragments be carrying not just chemical clues, but potential building blocks of life itself, drifting from one system to another like seeds of cosmic DNA? Those are the questions driving this global scientific chase, a race against time, light and distance, to understand something that doesn't belong to us, but now for a fleeting moment is passing through our neighborhood. From the moment 3I Atlas was confirmed as an interstellar object, every available telescope and spacecraft began racing to catch a glimpse of it. NASA's Mars Reconnaissance Orbiter MRO quickly adjusted its instruments, turning its powerful high-rise camera, a half-meter telescope, capable of capturing fine detail on Mars's surface, toward the comet's faint glow. Though the nucleus was too distant to resolve high-rise, aimed to detect subtle brightness. Variations flickers that could reveal how the solar wind and magnetic field were shaping its dust tail. At the same time, the European Space Agency redirected Mars Express and the ExoMars Trace gas orbiter. Their advanced spectrometers and cameras were calibrated to capture how sunlight interacts with the gases escaping from the comet. Even China's Tianwen-1, orbiting on the opposite side of Mars, joined in providing an alternate viewing angle. For the first time ever, Mars became a coordinated multi-agency observatory aimed at an alien visitor. The data flooding in is staggering. Early readings show that 3I Atlas emits primarily carbon dioxide, with a CO2 to water ratio nearly 80-1, a shocking discovery since most comets in our solar system are dominated by water vapor. This Yangdebao alone suggests the comet originated in an extremely cold environment, possibly near the outer edges of a distant planetary disk, orbiting a dim star where CO2 ice remains stable. In other words, is a frozen relic from a colder, darker system than our own. But that's not the only anomaly. Light-scattering measurements called polarimetric observations indicate that the comet's dust particles have undergone an extraordinary degree of radiation hardening. Over millions of years, exposure to cosmic rays may have compacted and darkened these grains, changing how they scatter light. It's as if the comet carries scars of its endless voyage through interstellar space. Scientists believe these physical and chemical traits could help us understand how planetary systems eject icy bodies, how they survive, transform, and possibly carry traces of their origin across the galaxy. But there's another reason why this Mars encounter is historic. The comet's trajectory placed it within a region of the solar magnetic field that's particularly unstable. If orbiters detect waves or distortions in the comet's ion tail, something that has never been observed directly from another planet, it would mark the first evidence of solar magnetic interaction with interstellar material. Such findings could reshape our understanding of how energy and matter flow between star systems, and whether these cosmic travelers act as bridges spreading dust and elements between worlds. The mission isn't just about curiosity, it's about perspective. For decades, humans have looked outward from Earth. Now from Mars, we're seeing something far older, far colder, and far stranger than anything native to our sun's realm. And this is only the beginning. As 3I Atlas continued its path toward the sun after brushing past Mars, the excitement among astronomers grew into something close to awe. Every few days, new readings revealed a story stranger than anyone had predicted. Unlike Oumuamua, which tumbled unpredictably without a visible tail, and unlike Borisov, which behaved like a familiar comet, this new visitor exists in a strange middle ground, an object both active and alien. Its tail reacts erratically to fluctuations in the solar magnetic field, creating ripples that could only be explained by charged particle interference. The orbiters near Mars are trying to detect these micro-distortions, hoping to capture the first direct record of interstellar material interacting with the sun's complex electromagnetic web. What makes this even more significant is that it's not a single probe observing from one angle. It's a network of instruments spanning multiple worlds. From Mars orbit, MRO's high-resolution imagery is complemented by ESA's spectroscopic data and China's wide-angle scans. At the same time, The James Webb Space Telescope, JWST, positioned nearly 5 million kilometers from Earth, has been monitoring the comet's spectrum, confirming the dominance of carbon dioxide, and detecting faint traces of exotic molecules that don't match the typical profile of solar system comets. This combined approach is what scientists are calling multi-point interstellar mapping, and it may become the model for how future missions track these fleeting travelers. Because if there's one thing 3I Atlas is teaching us, it's that speed is everything. These objects don't linger. They arrive unexpectedly, accelerate, and vanish beyond the heliosphere before we can even react. The fact that we managed to coordinate a multi-planet observation campaign within months of discovery shows how quickly humanity's scientific machinery can adapt when the universe offers a once-in-a-lifetime opportunity. But the deeper question remains: what does 3I our Atlas tell us about the diversity of planetary systems across the galaxy? Its chemistry suggests formation in a region rich in CO2 ice, possibly beyond the frost line of a low-mass dim star, or even a forming binary system. Its dust composition hints at prolonged exposure to radiation far more intense than the environment of our Kuiper belt. Together, these clues point to a birth in conditions unlike anything near our Sun. In that sense, every fragment of data we gather isn't just about one comet. It's about understanding what kinds of worlds exist out there, what kind of chemistry shapes them, and what processes eject such icy wanderers into interstellar space. And there's a philosophical layer too. As we watch an alien comet pass by our robotic emissaries orbiting another planet, we are seeing a collision of two frontiers, the farthest reach of human technology and the timeless drift of cosmic matter. It's a reminder that our solar system isn't an isolated bubble. It's part of a galactic ecosystem where material energy and maybe even the precursors of life are exchanged between stars. Soon, the Atlas will swing around the Sun, reaching its closest point, or perihelion, around October 29th to 30th, 2025. As it nears this fiery encounter, its activity is expected to surge dramatically. Gases will sublimate dust, will explode outward, and its coma could reshape entirely under the pressure of solar radiation. When that happens, we'll witness through the eyes of our orbiters the transformation of a frozen interstellar relic into a blazing torch, briefly illuminated before it fades back into darkness. The coming weeks will determine how much we learn or how much we lose to cosmic silence once it slips behind the Sun. By early November, the Atlas will disappear from Earth's view as it passes behind the Sun. But the story won't end there. The ESA JUICE spacecraft, currently en route to Jupiter, is poised to continue the pursuit. Between November 2nd and 25th, JUICE will observe the comet from deep space, giving scientists a perspective entirely different from that of the Mars orbiters or the JWST. This will mark the first coordinated study of an interstellar comet from multiple planets and a deep space probe, a milestone that signals a new era in planetary science. Each observation point, Mars-Earth's telescopes, JWST and JUICE, forms a network stretching millions of kilometers, each capturing how sunlight radiation and temperature alter the comet's chemistry over time. This approach allows cross-verification of spectral data, tail morphology, and isotopic signatures, subtle ratios of carbon and oxygen atoms that serve as fingerprints of the comet's birthplace. If those isotopic ratios differ even slightly from those found in comets of our solar system, it could confirm that 3I Atlas was forged around a cooler, perhaps younger star, a frozen emissary from a world that once orbited a faint red sun. But beyond the data, there's a strategic revelation here. The speed at which this observation campaign came together has reshaped how space agencies plan for future encounters. NASA's proposed Comet interceptor mission and ESA's similar studies are now being refined to ensure we never miss another chance like this. Because if the universe sends another interstellar messenger, and it will, humanity wants to be ready to meet it head-on. Yet scientists remain cautious. 3I Atlas is faint fast and difficult to image sharply. Most conclusions will rely on indirect measurements like fluctuations in brightness, gas emissions, and the behavior of its tail under solar stress. Even so, these fragments of information could redefine how we think about the galactic exchange of matter, how systems expel debris, how it travels for millions of years, and how sometimes it finds its way into ours. For a brief moment, Mars became humanity's outpost to another star. From that lonely red planet, we looked across the void and caught sight of something older than our entire civilization. A piece of alien chemistry brushed through our solar system, whispering stories from a place we may never visit. And just as quickly, it will vanish back into the dark, carrying traces of us, our reflections, our data, our curiosity, into the infinite cold. The question now isn't whether there are more like it out there. The question is, when the next interstellar visitor comes, will we be ready to chase it before it disappears again?